Hi, I'm James Smith.
And I'm Benjamin Tarnacki.
And we're here to talk to you about a nifty little enzyme by the name of sulfite dehydrogenase. Specifically, sulfite dehydrogenase found in a bacterium by the name of
Starkey novella. It is a soil bacteria. It can use a wide range of macromolecules and smaller molecules as carbon sources and energy sources. It can use things such as single carbon compounds, fatty acids, sugar alcohols, amino acids, and carboxylic acids as carbon sources and energy sources. And then it can use compounds such as DMSO and sulfite as energy sources.
But why do I care? A biochemist very near and dear to our hearts may ask. Well, there's lots of industrial applications with this particular enzyme. Sulfite is found in many foods and beverages and even pharmaceuticals as not only a preservative, but also as an anti-browning agent. So people who consume these products, who are just basically all of us, it's very important for us to be able to digest that enzyme properly through metabolism. It's also very important to study this particular enzyme because of asthma relief. Sulfite itself has been found to restrict the bronchioles of people who are suffering from asthma, so it's very important to have proper sulfite dehydrogenase activity if you're suffering from asthma. But it's very important to study this enzyme in and of itself because it has a molybdenum ion inside it, and it uses it as an active part of the active site inside of the activity of this enzyme. And so the enzymes that contain molybdenum are found in actually all forms of life. And so the more that we learn about this particular enzyme, the more we can learn about enzymes of every kind.
So this protein is a single gene protein. Its total DNA length is 1,293 base pairs, and its amino acid length is 430 amino acids. This makes sense because those extra 3 DNA base pairs are for the stop codon. This enzyme has 2 chains. One chain is for the 2 functional subunits of the enzyme, consisting of 373 amino acids. And then the other 81 amino acids are from cytochrome C550, which is an essential cofactor in this enzyme's reaction.
It also undergoes some very important post-translational processing, namely the addition of a heme group and a molybdenum cofactor. These 2 cofactors are added most likely through the help of heat shock proteins that allow that amino acid strand to fold in the correct conformation with the addition of the very important cofactors that help in the activity of the enzyme.
So our main paper is called Direct Electrochemistry of a Bacterial Sulfate Dehydrogenase. It was by Arge Zinsau, Bernhardt, Kapler, and McEwen.
It used protein voltammetry, the process in sending volts through a solution of enzymes and measuring the resulting current in amps. And it was interesting and very important because you are able to measure the activity of a particular enzyme at varying pHs without the use of substrate. And the electrodes used here were silver chloride, and a platinum electrode.
Then they also tested the redox potentiometry of the heme group, and this was done under standard methods of redox potentiometry. It was done in a glove box under a pure nitrogen atmosphere. Then they also used various mediators, oxidants, and reductants. The mediators used were phenazine methosulfite at sulfate at 1 micromolar, and then 2-hydroxy, the 1,4-methylquinone at 5 micromolar. Then the oxidant used was sodium sulfate, and then the reductant used was potassium iron cyanate.
But why do we care? A biochemist very near and dear to our hearts may ask. Well, this particular experiment was unprecedented in its time. Protein voltammetry had never been done with a molybdenum ion containing enzyme, and so that paved a new way for all molybdenum containing enzymes, as this protein voltammetry method was able to be used with them as well. At the time, the year that this main paper was written was 2002.
So this is the flowchart for our main enzymes reaction. So it starts out molybdenum 6, iron 3, takes a sulfate, turns it into sulfite. The molybdenum becomes molybdenum 4, and you still have iron 3. Through an equilibrium reaction, the molybdenum donates an electron to the iron, becoming molybdenum 5 and iron 2. Cytochrome C comes in and takes an electron from the iron, turning it back into iron 3. Another similar equilibrium reaction happens, and it turns into molybdenum 6 and iron 2. Cytochrome C comes in yet again, takes another electron from the iron, we're back to molybdenum 6 and iron 3.
And this is the same mechanism shown previously, but broken down into the 5 steps that it goes through. And we're going to break down these steps and show some error pushing to show exactly what happens in the active site and exactly how this enzyme metabolizes sulfite.
So first up, the sulfite does a nucleophilic attack on the oxygen that is double bonded to the molybdenum. Two of the electrons that are bonding the molybdenum to the oxygen actually go to the molybdenum, turning it from molybdenum 6 to molybdenum 4. And the reason the molybdenum can accept these electrons is because it's a transition metal and has that extra d orbital to accept those electrons. Additionally, this oxygen right here comes down and forms a double bond right here. Here, making this product right, this intermediate right here. Since the molybdenum has actually done chemistry, this is metal ion catalysis, and since this oxygen is covalently bonded to the molybdenum, it is also covalent catalysis.
In this step, there's a lot going on, but the most important step here is the electrons moving that are responsible for the bond between the molybdenum 4 and the oxygen moving onto the oxygen here, resulting in our sulfate 2- here. While that happens, water is deprotonated, and the electrons on the oxygen inside the water then occurs using a nucleophilic attack on molybdenum 4, forming an alcohol group here. But the interesting thing here is shown that during this particular step, the subunit containing the heme group with the iron here actually swings around and forms a temporary different conformation inside the enzyme, allowing the iron to steal one electron from the molybdenum, resulting in molybdenum 5 here. So the result here is a acid-base catalysis on the water, a covalent catalysis by breaking that particular bond between the molybdenum and the oxygen here, and metal ion catalysis as the electron is moved from molybdenum to iron here, resulting in molybdenum 5, iron 2, sulfate, our product here, and a hydrogen proton.
So now that our enzyme is done doing its actual chemistry, it needs to re-equilibrate itself. It starts doing this by having cytochrome C550 come in and take an electron from this iron, turning it back into iron 3, and making cytochrome C552.
In this step, it's important to focus on the molybdenum 5 here and the OH. This alcohol group is deprotonated and turned into a carbonyl group on the other side. During this time, an electron again is stripped off from the molybdenum and added to the iron during another swing around, and that results in a molybdenum 6 on the side and another hydrogen proton. This is more acid-base catalysis and metal ion catalysis, since there is electron transferring between the molybdenum and the iron in the heme group.
Then step 5 is very similar to step 3 in that it again involves cytochrome C coming in, taking an electron from the iron, and turning it back into iron 3. And now we're back at molybdenum 6, iron 3, and the molybdenum is double bonded to this oxygen, meaning we're back at our original enzyme state.
So here's our circle, one more time. We have molybdenum 6 and iron 3 here. It undergoes one single step that we've broken into two substeps, turning the sulfite into sulfate, and which also results in molybdenum 6 turning into molybdenum 4 and iron 3. Then it goes through an equilibrium reaction that is heavily favored in the forward direction into molybdenum 5, iron 2. Cytochrome C550 at the 3 charge accepts an electron from the iron, resulting in a cytochrome C2, a molybdenum 5, and an iron 3. It then goes through another equilibrium reaction, turning that into molybdenum 6, iron 2, and then the cytochrome C accepts yet another electron, turning that into our original state of molybdenum 6 and iron 3.
So this mechanism relates to our paper very well, since they were testing for the electrochemistry of the enzyme. And as you can tell from the mechanism, there's a lot of electrochemistry that was going on. All of the fluxes of the oxidation states of the molybdenum from 6 to 4 to 5 back to 6, and then the iron constantly back and forth from 2 to 3 to 2 to 3.
And so electrochemistry is an excellent tool to use to measure the activity of this particular enzyme, because of all the electron transferring and the equilibrating back to its original state results in different potentials and different amps in response to volts in this particular enzyme.
Oh. Sorry, a little malfunction there. So Our paper actually ended up helping prove the optimal pH range of this enzyme, and you could actually see that in step 4 if you were paying very close attention and really knew your chemistry. So step 4 is an equilibrium reaction, and one of the products is H+. So under pH 7, you're going to have way too much H+ in the solution to make this equilibrium very favorable for this product. And instead, under pH 7, it's going to heavily favor this instead of the product that you want. So you'll notice that when we show our turnover number values table, the turnover number, or once you get past pH 7, plummets dramatically. And then the scientists actually did elicit a non-turnover voltammetric response in this enzyme, which means they got electron transfer with no substrate present, which was completely unprecedented at the time this paper was written. So here are the figures of our paper. This figure 1 is the cyclic voltammograms of sulfite dehydrogenase on 2 different kinds of electrodes. And you can see here that even with no substrate presence, they did get various voltammetric responses from both ion pairs. Then this is testing voltammetric responses at various pHs, and while at lower pHs with no substrate, they did get electron transfers. This doesn't happen with actual substrate because the equilibrium reaction just isn't very favorable at lower pHs, and then this table is the exact values from this graph.
And so this shows the optimum pH that this particular enzyme works at. And you can see that the change here is pH, and the dependent variable is amps, resulting from the solution. And you can see around 8.5, the optimum pH for our particular enzyme. And as highlighted below, before, around pH 7, below that, there's nearly no activity of this particular enzyme due to the acid-base step required in its activity. And here are some important bioinformatics for our enzyme. The PI, or isoelectric state, isoelectric point, is 5.5. The subpoints alpha and beta together form an enzyme with a total of 49.4 kilodaltons. The alpha is 40.6 kilodaltons, and the beta is 8.8 kilodaltons. And there's a very important electrostatic interaction between these 2 particular subunits because they don't covalently bond together. They only form together out of electrostatic interactions, which allows that heme group, that heme-containing subgroup, to be able to swing into that molybdenum-containing subgroup and steal an electron from that twice during our reaction. The pH range of any activity that we found from this enzyme ranges from 5.5 to 9.4, and the conserved domains between sulfite dehydrogenase for Sarconovella and humans and other different kinds of animals and bacteria include in arginine at the 5.5 range.
At 55.
At 55, thank you. The histidine at 57, and the tyrosine at 236. And so this is our Km table showing that the higher our pH goes here, the higher our Km goes, depending on the pH of our tris acetate buffer,
And you can see that at pH around 9.4, you see your Km really starts to go down, which means that's where your optimal affinities are.
And here's our turnover number table. And you can see that at pH range of 9.5 to 8.5, you have our highest turnover rate. And if you get below 7 here, you have a significant drop. And at pH 10 over here, you can also see very little activity due to the acid-base nature of this particular enzyme.
And then here is 2 images of the active site in two different time counts and models taken from the same modeling software. This is the more string type, and you can very clearly see the heme group right here and the molybdenum group right here. However, when you do the space fill model, with all the electron shells, you can see that the iron in the heme group is much too sterically hindered to do any actual chemistry, and the molybdenum group is peaking out right here, very able to do actual chemistry. And then there's a lot of similar enzymes. Xanthine oxidase and DMSO reductase are both enzymes that were mentioned in our paper, and they're both molybdenum reductase enzymes. Then in Uniprot, there's two particular enzymes that caught my interest that were of about 50% similarity. You had a nitrate reductase, also known as NADH, from methylboron extorquens. That was about 50% similar, and then from another bacteria of the same family, Methylboron populi, its sulfite dehydrogenase enzyme is only about 50% similar to ours. And then here is one page of our references. And
here's the
page
second
2 of
page.
our references.
Hi.